All right, let's dive into some serious quantum weirdness today. We're tackling entanglement swapping, a concept that sounds like it's straight out of Star Trek. But trust me, this is real science with huge implications for the future.
It really is. It's one of those ideas that forces you to rethink what you thought you knew about reality.
Exactly. We're going deep into an essay by Yorgo Schneppert, who lays out this mind-bending concept with impressive clarity. So to kick things off, what exactly is entanglement? It's kind of the starting point for this whole entanglement swapping thing, right?
Absolutely. Entanglement is this bizarre connection between two particles where no matter how far apart you separate them, measuring one instantly tells you the state of the other.
Okay, that already sounds pretty wild.
Yeah.
But how can we be sure this isn't just some coincidence? Schneppert mentioned something about Bell's theorem proving this is a real quantum phenomena.
Right. See, back in the day, some physicists thought there might be hidden variables we just weren't seeing that were determining the states of these particles. But Bell's theorem shows that the correlations we see between entangled particles are so strong that they can't be explained by any classical theory that relies on local realism. Basically, it rules out those hidden variables.
So actions on one entangled particle really do affect the other instantaneously, even across vast distances. That's crazy.
It is. Einstein himself famously called it spooky action at a distance because he was so troubled by the implications. But decades of experiments have confirmed that entanglement is a real and fundamental aspect of the quantum world.
Okay, I think we've got a handle on entanglement itself. So now for the main event. What is entanglement swapping and how does it work?
Imagine you have two pairs of entangled particles. Let's call them A, B, and C, D. Now, without ever letting A and D directly interact, we can actually entangle them. We do this by making a special kind of measurement on particles B and C.
Hold on, back up. How does measuring B and C do anything to A and D, which have never even met?
It's all about projection. Think of it this way. When you measure B and C in a very specific way, you essentially force them into a particular entangled state. And because B was initially entangled with A and C with D, this measurement projects A and D into an entangled state as well, even though they were never directly linked before.
So we're not directly manipulating A and D. We're manipulating their partners and letting the existing entanglement do the heavy lifting.
Exactly. And that's the beauty of entanglement swapping. We can create entanglement between particles that have never interacted directly simply by manipulating their entangled partners.
Okay, this is starting to click. But I'm still wondering, what's the point of all this?
Right.
Why should anyone care about entangling particles that were never together in the first place?
Well, that's where the real-world implications come in, and this is where it gets really interesting. Entanglement swapping isn't just a cool scientific curiosity, it's the key to unlocking some truly groundbreaking technologies. Think unhackable communication networks, powerful quantum computers that can work together across vast distances.
Whoa, hold on. Are we talking about real-world applications here, or is this still sci-fi territory?
It's both. These technologies are still in their early stages, but the potential is enormous, and entanglement swapping is at the heart of it all. Think about it. If you could create a network where information is transmitted using entangled particles, it would be inherently secure. Any attempt to eavesdrop would disrupt the entanglement, instantly alerting the sender and receiver.
That sounds incredible, like something straight out of a spy movie.
Yeah.
But how would entanglement swapping help with quantum computers?
Quantum computers, unlike your laptop or phone, rely on quantum phenomena like superposition and entanglement to carry out computations. And entanglement swapping allows you to connect these quantum computers together, creating a quantum internet capable of tackling problems far beyond the reach of classical computers. Think drug discovery materials, science-breaking complex codes. The possibilities are mind-boggling.
Okay, I'm officially on board with the mind-boggling part. But this all sounds incredibly complex. Schneppert mentions some real-world examples of entanglement swapping already taking place. Is this stuff actually happening in labs, or are we still in the theory stage?
Oh, it's happening. Researchers have been demonstrating entanglement swapping in labs around the world for years using clever techniques with photons, lasers, and detectors. Pioneers in the field like Elaine Aspect, Anton Zeilinger, and Jianwei Pan have made groundbreaking contributions to proving and refining this process.
So it's not just a theoretical possibility. We're actually making entanglement swapping work.
Absolutely. And the pace of progress is accelerating all the time. It's a truly exciting time to be following this field.
I can imagine. But also have to imagine it's not all smooth sailing. Schneppert mentioned some challenges and open questions too, right?
Right. Even though we've come a long way, there are still some significant hurdles to overcome before these technologies can become commonplace. One of the biggest challenges is decoherence.
Decoherence? What's that?
It's basically the tendency for entangled particles to lose their delicate connection when they interact with their environment. The longer the distance and the more complex the system, the harder it is to maintain entanglement. Imagine trying to keep two soap bubbles linked together in a hurricane. It's incredibly difficult.
So the more complex we make these systems, the harder it is to keep the entanglement stable. That makes sense. But are scientists finding ways around this?
They are. There's a lot of research going into developing new materials and techniques to shield entangled particles from their environment and minimize decoherence. They're also working on ways to correct errors that inevitably creep in during quantum operations. It's a constant race between the possibilities and the limitations.
It sounds like it. But from what you're saying, it seems like the possibilities are worth chasing.
They absolutely are. As Schnepphat emphasizes, entanglement swapping is not just some obscure scientific concept. It has the potential to revolutionize how we communicate, compute, and even understand the universe itself. It's a fundamental shift in our grasp of reality, and it's happening right now.
All right, before we get too lost in all the mind-blowing implications, let's take a step back and revisit some of the specific details of how entanglement swapping works. This is where understanding those real-world experiments comes in handy.
Agreed. Let's delve into those pioneering experiments and see how they brought entanglement swapping from theory to reality.
Sounds like a great place to pick up in part 2. Stay tuned.
So as we delve into these groundbreaking experiments, it's fascinating to see how they've taken entanglement swapping from a theoretical concept to a tangible reality.
Absolutely. Schnepphat highlights a few key experiments. Let's start with Elaine Aspect's work back in the early 80s.
Yeah.
What made his experiment so important?
Aspect's experiment was a pivotal moment in our understanding of entanglement. He used a clever setup involving entangled photons and strategically placed detectors to rule out any explanations based on classical physics. His findings essentially solidified the idea that the correlations we see in entangled particles can't be explained by any local realistic theory, meaning there's no hidden information dictating their behavior.
So he really drove a stake through the heart of those hidden variable theories. That must have ruffled some feathers in the physics community.
You could say that. It was a significant departure from the classical worldview and really cemented the non-local nature of quantum mechanics.
Wow, that's huge.
Yeah.
Okay, so Aspect laid the foundation. What about Anton Zeilinger? Schnepphat mentions him as a key player in entanglement swapping, too.
Zeilinger and his group really took entanglement swapping to the next level. They were among the first to demonstrate the process experimentally, proving that it wasn't just a theoretical possibility. They showed how a specific type of measurement on one pair of entangled photons could remotely entangle two other photons that had never interacted before.
Could you walk us through how that works on a practical level? It still seems like quantum magic to me.
Imagine you have two pairs of entangled photons. A, B, and C.D. Zeilinger's team cleverly entangled the polarization of these photons, meaning their light waves oscillate in specific directions. They then performed a joint measurement on photons B and C in a way that projected photons A and D into an entangled state, even though they were physically separated and had never interacted before.
So by carefully selecting the type of measurement on B and C, they essentially dictated the entanglement fate of A and D. That's incredibly subtle and powerful.
It is, and this ability to remotely entangle particles that never interacted directly opened up entirely new avenues for quantum communication and computation.
Schnepphat also mentions Yanwei Pan and his team as major contributors. What were their breakthroughs?
Pan's team has been pushing the boundaries of entanglement swapping in terms of distance and complexity. They've performed experiments demonstrating entanglement swapping over incredibly long distances, even using satellites to beam entangled photons between ground stations hundreds of kilometers apart.
Oh, wait, they're using satellites to swap entanglement. That's some next-level science fiction stuff.
It is. Their work is crucial for understanding the challenges and possibilities of building large-scale quantum networks that could span continents or even the globe.
This is all incredibly impressive, but I'm curious about the practical limitations here. Could we theoretically entangle particles across galaxies? Where do we draw the line?
That's a great question, and it highlights one of the key challenges. Decoherence. Remember our soap bubble analogy. As entangled particles interact with their environment, their delicate connection weakens. And the farther apart they are, the more opportunities there are for that connection to be disrupted.
So even though entanglement itself might not have a distance limit, practically speaking, it's incredibly difficult to maintain over vast distances.
Exactly. Maintaining entanglement across galaxies is a daunting task with our current technology. The signals would be incredibly weak and susceptible to interference from the vast expanse of space.
It sounds like there's still some major hurdles to overcome before we're beaming messages across the cosmos using entanglement. But the progress made so far is still remarkable.
It is. And even if galactic entanglement swapping is a long way off, the implications of what we're learning now are profound. As Schneeppert points out, these experiments are not just about technological advancement. They're pushing us to reconsider our fundamental understanding of reality.
Okay, that's a perfect segue to my next question. Schneeppert mentions some mind-boggling questions about the role of entanglement in the universe. What are some of the big ones that scientists are grappling with?
Well, for starters, does entanglement suggest that our universe is fundamentally interconnected in ways we're only beginning to grasp? Could it play a role in explaining the mystery of dark matter or dark energy? And perhaps most intriguingly, could entanglement play a role in consciousness, or even the origins of the universe itself? These are big, profound questions that we're just starting to explore.
Wow, those are some heavy implications. It seems like entanglement swapping is not just about building faster computers or more secure networks. It's about probing the deepest mysteries of existence itself.
Precisely. And as we delve deeper into these experiments and their findings, we'll undoubtedly uncover even more questions and possibilities that we can't even fathom right now.
Well, I'm officially hooked. Schneeppert has definitely given us a lot to chew on. What else does he explore in his essay?
He delves into some fascinating thought experiments, pushing the boundaries of what might be possible with this technology. For instance, could we use entanglement swapping to teleport objects, or even consciousness across vast distances?
Hold on. Teleportation. Is that even remotely possible?
It's a fascinating concept. Teleportation in the quantum realm isn't about physically moving matter from one place to another. Instead, it's about transferring the quantum state of a particle, including its entanglement, to another particle that's located elsewhere.
So it's not beaming Captain Kirk across the galaxy, but more like copying his quantum blueprint onto a new set of particles at the destination.
You got it. And while teleporting something as complex as a human is still firmly in the realm of science fiction, scientists have successfully teleported the quantum states of photons and even atoms.
This is definitely bending my brain a bit. And Schneeppert suggests this could be applied to consciousness, too.
He raises the question, which is certainly thought-provoking. If consciousness is somehow encoded in the quantum state of our brains, could we theoretically transfer that state to another substrate? It's a highly speculative idea, but one that highlights the potential for entanglement swapping to revolutionize not just our technology, but our understanding of ourselves and the universe.
Okay, I'm definitely going to need some time to process all of this. But before we get too philosophical, let's bring it back to the concrete ejection. Schneeppert spends some time discussing the specific techniques and technologies used in these entanglement swapping experiments. I'm curious to learn more about how they actually make this stuff happen in the lab.
Absolutely. Let's dive into the nuts and bolts of these experiments and see how these brilliant minds are turning quantum weirdness into groundbreaking science.
All right, let's get down to the nitty-gritty. Schneeppert dives into the actual techniques used in these entanglement swapping experiments.
Yeah.
What are some of the tools of the trade here?
Well, photons play a starring role. They're these tiny packets of light that are relatively easy to generate, manipulate, and detect. Plus, they're not as susceptible to environmental noise as some other quantum systems.
So it's all about harnessing the power of light. It's kind of poetic in a way.
Yeah.
But how do they actually entangle these photons in the first place?
There are a few different techniques, but one common method involves a special crystal that can split a single photon into two entangled photons. These photons are then sent along separate paths using mirrors and optical fibers.
Okay, so we've got our entangled photon pairs. What happens next?
That's where the clever measurements come in. Schneeppert talks about Bell state measurements, which are designed to reveal the entanglement between photons without destroying it. These measurements involve combining the photons from the two different pairs at a special kind of beam splitter.
Beam splitter, is that like a microscopic traffic intersection for photons?
It's a good analogy. It's a device that can either reflect or transmit photons depending on their polarization. By carefully analyzing how the photons interact at the beam splitter, researchers can determine whether the original pairs were entangled and project the remaining photons into a new entangled state.
That's fascinating. It's like they're choreographing these tiny particles of light to dance in a perfectly synchronized way. But Schneeppert also mentions some of the challenges in keeping these experiments running smoothly.
Right, these experiments are incredibly sensitive. Even the smallest vibration or temperature fluctuation can disrupt the delicate entanglement. That's why researchers often work in highly controlled environments using ultra-precise lasers and detectors, shielded from external noise.
Sounds like they're trying to build a house of cards in a windstorm.
Yeah.
But I guess that's the nature of working with quantum phenomena. It's so delicate and counterintuitive.
It is, but that's part of what makes it so captivating. As Schneeppert points out, these experiments are pushing the limits of our technological capabilities and forcing us to confront the profound strangeness of the quantum world.
It's a constant reminder that we're still just scratching the surface of what we know about the universe. And it makes you wonder what other mysteries and possibilities are out there waiting to be discovered.
Absolutely. Entanglement swapping is just one piece of the puzzle, but it's a crucial one. As we continue to refine these techniques and push the boundaries of what's possible, we're opening up entirely new avenues for exploration and innovation.
Well, I, for one, want to thank Jörg Schneeppert for taking us on this incredible journey through the world of entanglement swapping. It's been a truly mind-bending and inspiring experience.
Absolutely. It really highlights how significant these scientific discoveries are.
And to our listeners, we hope this deep dive has sparked your curiosity about the wonders of quantum science. Until next time, keep exploring.